let me explain to you what you're about to see. I've done several workshops on problem-space analysis here and at other shows, and I've taught it outside of the shows as well. But the trouble is that every time I've ever done it, it's been a really big thing. It's been a whole day, or it's been 2 days, or it's been a week. And I thought, well, I and the conference organisers thought, well, it might be quite nice to do an introduction just to explain to people what this is about and to show you why you should be interested in this and why you should come back tomorrow and do this all day. Come on in. Has anybody heard of this stuff before? Does anybody know what problem space analysis is? Okay, so why are you here? No, seriously, I'm curious. I mean, let me ask one other question. Who here would describe themselves as architects? Okay. Team leaders, project managers, and humble developers. Okay, that's what now, this computer has been playing for me. Okay. Now, those of you who are working in developers particularly, but architects as well, I want to ask you about the environment you work in. How many people are doing a process which is called agile? Even if it's only Scrum, which isn't agile, but... Okay. Now, I'm going to come back to you guys. Who is still doing waterfall or command and control or something like that? Nobody. Okay, so a lot of you aren't doing anything at all. Anybody doing any process that isn't either of those that you describe as distinct? Okay, what are you doing?
It's kind of vague in the middle. We work on tasks,
Right.
but there's a team of kind of 5 or 6 of us, and people move between projects and what needs to be done. Effectively, we've got 2 different product managers deciding what to do, so they agree with themselves. It's agile-ish, but other than kind of agile.
Okay. Is it working for you?
Yeah, it does. I mean, when the product managers pressures change, hours change, but it does work. Get things done. We've always got to work on.
Okay. All right, you guys who are doing agile, I've got a question for you. Those are the ones who put up their hands first. Is that working for you? I mean, the promise of agile, right, is that you can produce a lot of value very quickly, highly reliable. Are you doing that? Anybody?
Most of the time.
Really? Okay, one person. Now, this is funny because in the course of the work that I've done, I'm a contractor, so I've seen an awful lot of development. I've seen a lot of waterfall-y type development, and I've seen a lot of agile type development. I've seen a lot of projects fail, and I've seen a lot of projects succeed. And as far as I can tell, the difference between a successful project and an unsuccessful project is not how agile it is. In fact, that seems to have no relation to the outcome at all. The actual success factor, the real fairy dust that makes it work, is something else entirely, and it's completely independent of your methodology. Now, part of what problem-space analysis is about is to try to understand what that is, and to try to characterize it. Has this worked? Good. Now, I'm going to shut the door now, because they're not here by now, it's too late. Now, there's something I want to talk about here, and that's horizon. Developers, particularly agile type developers, have a horizon of a couple of weeks. That's the size of the sprint. So you know what you're doing for the 2 weeks. Theoretically, you're not supposed to know what you're doing following them. Okay? If you're working on it as a team lead or a project lead, you've got a much longer horizon. You've got a sense of a business requirement that you have to bring in. It's not a tiny atom of value. It's not a minimum viable proposition. It's something rather larger than that. So generally speaking, the horizon there is six months to 2 years. Generally these days we're trying to get it shorter. We're trying to aim towards the 6 months. Okay? And then you have to look at architects. And you come to the architecture conference, everyone's arguing what's the difference between an architect and a developer and a team leader and just a boss. And this is the difference, it's the horizon. So what's an architect's horizon? 6 months? No, way more than that. 5 years, maybe 10 years. Sometimes 30 years. Those of you who can remember the Millennium Bug before, the whole point about the Millennium Bug was that we had got deeply embedded in all of our code bases that was 40 years old and written even before people could count up to 2000. So the thing about an architect is that he is trying to predict the future 30 years ahead, potentially. How can he possibly do that? The whole point about Agile is that, well, you can't trust the specifications because it'll change the specifications before the ink's dry. And yet, we've got architects who are trying to predict 30 years ahead. How is that even possible? But it is, because you can tell the difference between a good architect and a bad one. So, this fairy dust, this thing which makes the success factor, this is the thing which the good architects do, and the bad architects don't. And actually, the developers are not looking at because they've still only got this 2-week horizon. So that is what problem space analysis is all about. Now, again, before I get into the meat of it, I want to show you. I would like to talk a bit about reliability. I care very much about reliability. If you've been to any of my other talks, you'll know how much I care. But you often see pictures like this. What we've got here is a sense of how much it costs to fix a defect. So you've introduced a defect at one point, and then it's malfunctioned at some other point, which is the point at which you're going to fix it. Do you understand the difference between a defect and a malfunction? Anybody not clear? Okay, thank you. That gives me an excuse to explain. If you're driving a car, and everything's working fine, and then suddenly, and it's all over the road. This has happened. The car is now malfunctioning. It's not steering properly, or it's not going properly, or whatever it is. But it's malfunctioning, and you know it's malfunctioning because it's not doing what you wanted to do. It's not steering along the road, or it's not accelerating properly. So you are understanding the fault in terms of its failure to function. But somewhere else, there is the explanation of that. So there's a linkage broken, or there's a pipe come off, or something like that. That's the defect which has given rise to the malfunction. And this almost always is a fault, it's a break, it's a fracture in a vehicle. Now in software, things don't break. If we've got defects, then they're there because somebody put them there. But you still have this separation between a malfunction and a defect. The malfunction is how you know it's gone wrong, and the defect is the cause of that malfunction. Now you can't have a malfunction without a defect, but you can have lots of defects without malfunctions. You know this. You know that you can write your code and you test it and it's fine and you put it into production and suddenly it's crashing and burning all over the place. It's malfunctioning like hell, and you can trace it back to a defect that was there all along. But it hasn't caused a malfunction until you released. Now let's look at the cost of this. Let's suppose we introduce the defect at the coding stage. And you'll see various versions of this picture, by the way. You'll see different multiplication factors, you'll see different stage names. It doesn't matter. The basic story that this picture is telling you is absolutely consistent and has been replicated many times over. So, you introduce the defect, you discover the malfunction, you try and recover the defect, it costs you an hour, that's $25, something like that. So, it's a nice, simple, easy fix. But let's suppose you don't find it there. Let's suppose you throw it over the wall to test, and they have to find it. And so now, they're doing the test, and they find it, and they write a report, and they hand it back to you, and you've got to stop what you're doing, and now you've got to find the defect, and you fix it, but now you fix it. Now that costs you maybe 5 times as much. Okay? Let's suppose they miss it. Let's suppose you get it into production, or you put it out in the wild, and it's your customers who find it. Now, that's very much more expensive. Now you've got to go all the way back to the coding, and you've got to try and fix it at that level. And now, it's costing 125 times as much as when you started. And we all know this. The later you find the defect, the later you elicit the malfunction, the more expensive it becomes. No problem with that, right? But here's what's interesting. This is true right across the production chain, or right across your development chain. The earlier you introduce it, the later you find it, the more it costs. So if you get your architecture wrong, and you don't discover until you hand it out to the customers, boy, are you in trouble. And if you get your requirements wrong, and you don't discover it until here, then this multiplier is generally of the order of the cost of the project itself. If you built the wrong thing, you've imperiled the whole project. Now, just to make it clear, this is a logarithmic scale. What this chart actually looks like is this, and that is going up and interfering with the flight path out of Heathrow. So that's why this buggers up your project. Now, look at this. We all test our code. as we're writing it. And we test it furiously. We have regression testing, we have integration testing, and then we toss it over the wall to a test department who are testing it. We care about this, and we care about these costs. But if we had any brains, we would be testing our architecture, and we would be testing our requirements with the same, if not more, assiduity as we test our code, because this is where the real damage is done. And yet we don't. And the reason why we don't is that by the time we get to code, we've now got something formalized, something testable, something that you can run. And it's the first time at which we've got it. There's a sense in which this is the first moment at which we can test. And if we try to test it, how can you test an architecture? It's a load of pictures on a wall and people with long hair waving their arms around. And as for the requirements, well, it doesn't make any sense at all. And yet, all the risk is over here. So, is there some way in which we can figure out what these, where we can look at our architecture, where we can look at our requirements, and we can say, yes, this is actually what we want to build, in spite of the fact that we're operating in a world of change. If we can do that, then we can get a very high degree of safety right the way through the rest of the development. And we can get the promise that architecture really, we can deliver the promise that architecture claims to be able to deliver. Does that make sense? Now, I know I haven't told you yet how to do it, but you understand the argument. Does anybody want to challenge me on this? Okay, good. But this is our problem. Change is a fact of life. The whole principle behind trying to write a specification, it says, this is what we're going to build, and this is what we're going to test against at the end, and if they don't match, then we've got it wrong. And yet, we know that specifications change. Actually, there's a very good reason why specifications change. It's in the nature of software itself. What happens is, when you start working on a problem, what you tend to do when you're writing a program, you're trying to take a manual process of some kind and you're trying to automate it. Ultimately, all programming boils down to that. You're trying to automate something. And that means that having taken that problem and automated it, it's no longer your problem. And when you've got rid of your number one problem, guess what? Number two gets a promotion. Now, this is important. This is a process called emergence. It's what turns physics into chemistry, and what turns chemistry into biology, and what turns biology into sociology. And at each stage, not just do the problems change, but the whole language, your whole mental approach to the problems have changed as well. Now, when our specifications change, it's because we've got these new problems emerging. And that's the proof that we're solving the old ones correctly. Change is not a bad thing. Change is not only the way Agile presents it, they say that change is the problem that we have to solve. No. Change is evidence that we're solving it. The real problem is something even bigger, but the fact that it's changing is so important. We can't deny that, so we can't go back to pure waterfall. So, this is what we appear to be trying to do. We have this task that we're trying to solve, and we're always trying to catch up with it, and we're always like one step behind. And this is true either in a waterfall model or in an agile model or anything else. And it's the fact that that fly is a moving target. That's what stops us from being at all formal about our specifications or our architecture. So that, what you just saw, is the problem that we have to solve. Would you like to see my fly again? Because I spent ages animating that. Okay, maybe not. Now, none of our existing methodologies address that problem correctly. Craftsmanship, this is the idea that you can get good at something by doing it over and over again, which you can. Ask a musician, ask a woodcarver. But what that does is it actually denies change, because the musician says, I'm going to perform this 100 times so that the 101st performance is perfect. The woodcarver goes over and over again so that it's perfect each time. So he's saying, I am trying to solve the same problem over and over again. How many people in this room have solved the same problem even twice? Enough said. Waterfall impedes change. You've got this plan, you're starting building to the plan, and somebody says, that's not exactly what I want. Okay, that's fine, we can cope with that. What you need to do is fill out this change document. You need to send it to him, he's going to photocopy it, he's going to send it to all these different people. They don't know what they're doing, so they're going to form committees to discuss them. It'll come back to you in 6 months' time. That's fine. So the whole process of waterfall is to impede the process of change. It's designed to do it. And it's why it doesn't work in software, but it's why it does work in something like avionics. Because in avionics, you want to be absolutely sure what you're building. But what about Agile? Agile suffers from the opposite problem. Agile is completely adrift on change. It's like a ship with no sail. It's just swept by the tide. And the fact is that every software project does actually have an aim in mind. We do know, somebody somewhere knows what we're aiming for. There's a business problem to be solved, there's costs to be met. I mean, you can't just completely let go and say, well, we'll go wherever the wind takes us, because that doesn't actually get you where you want to go. It gives you a very nice meander, it's tremendous fun to work in it. But in commercial terms, and even in terms of validation terms, if you're not bored after 2 years doing that, then you've got no brain. So what you need to do is, even with Agile, Agile is not addressing the change problem. Change it exists, but it's not our master. It's simply one aspect of the problem. But, although specifications change, okay, I'm going to put this up now. So, change is not part of our problem. It's not the thing which stops us from solving our problem. It is the problem. It's the thing which we have to address ourselves to. This is really basic stuff. I'm not challenging you at all here, am I? But there is something very interesting here. And that is, well, let's talk about what these changes are. Because we can talk generally about change, and I've never heard anybody actually unpack what these changes might be. So let's try this. There are obvious changes. And you already know about obvious changes. You already know that if you've got constants or passwords or URLs, you don't put them in the code, you put them into constants or even in configuration files, because you know damn well they're going to change. And you don't want to change them out through the program. There are changes which are just plain stupid. Now, I'm going to give you some examples of that in a minute, but things that you're just never ever going to want to do. So these are not our problems, because we already know how to cope with these. And we're never going to cope with these. Our problem lies in between. Our problem lies with these surprising changes, which in retrospect you go, oh, damn, I should have thought of that. But you don't, because you just get blindsided by them, and they're perfectly obvious in retrospect. This is the problem that we're trying to solve. How to predict these surprising problems. How to predict the things that up until now we can't predict. And we need to do this at an architectural stage, at a requirements gathering stage. Now, how do we detect those? How can we predict the unpredictable? Well, the answer is that they are not unpredictable. There's a very interesting difference between these problems and these problems, or between those two changes. It's this. The specifications will change, the requirements will change, but the language in which they're written will never change. There is basically some intellectual foundation which holds these specifications together. So let me give you some examples. Let's suppose we're building an accounting system. It's possible that you're going to want to add different kinds of stops, or different kinds of credit limits for different kinds of customers. It's possible that you're going to want to introduce multi-currency accounts. It is not possible that you're ever going to use it to defeat the evil Quag Empire. Try this one out. This is a real one. If you're building an avionics system, this is where I got started, you're very interested in mass, in moments, in thrust vectors, and all of those sorts of things. You're very interested in fuel consumption. You're really not very interested in the number of chocolates on board. I actually saw somebody try to put that into a specification one time. Another field that I used to work in, oil. We're very interested in holes in the ground. We're very interested in wells. We're interested in their length. We're interested in the diameter. We're never going to play tunes on them. So here's the thing. If we're going to try and handle the change, then what we need to do is not say, what's changing about the specification? What's the specification going to turn into? What we need to say is, well, what is this intellectual foundation which underpins the expression? Not, do we believe the specification? Of course we don't believe the specification. Of course it's going to change. We want it to change. But we don't have to believe the specification. What we have to believe in is what has to be true to make the specification even make sense. Does that make sense? Would you like me to expand on that, or would you like me to carry on? In that case, prompt me. What more would you like me to say?
Could you repeat again?
Yes. We don't care about the truth of the specification. We don't care whether it's right or wrong or how long it's going to last, because we know it's not going to last. We know they're going to change.
Yeah.
And if they don't, we will. But the one constant, the thing that we do care about is what needs to be true for the specification even to make sense. What's the thing, what's the intellectual foundation, what's the conceptual structure which underpins the specification? Because they will ask for different kinds of accounts. They'll ask for different kinds of currencies. They might even ask for different kinds of names or different kinds of account holders. But they're not going to change the fundamental nature of what an accounting system is. Not ever. So we are very, very interested in this underlying language, in this underlying conceptual structure. Well, I am, and I hope by the end of the day you are. Right, so let's go back to our fly. What does this mean in terms of in terms of that analogy? Well, it means this. It means instead of trying to chase the fly, we wait for the fly to come to us. We delineate the space in which the fly is allowed to be. And eventually it will come to rest. And when it's come to rest, we've already covered all of that space. Our specification, our software, our architecture, everything is not that. It's that. And so it doesn't matter where the eventual specification settles. We've already got it covered. Now, that is a future-proof architecture. So how do you find that? Let's talk some more about the problem space. The problem space is well, there's lots of ways of approaching it, and I'm going to be a bit wishy-washy about this. These are not different things. These are all different ways of trying to say the same thing. And it's quite a hard thing to describe because it is a bit of a wishy idea. This is the atomic foundation of the specification. Now, by that, I mean you need certain fragments of knowledge, certain fragments of ideas, which in and of themselves aren't complete, but when you put them together, form a coherent idea. When you talk to domain specialists, they will use these atoms all the time. Dawkins talked about memes, and there were very similar sort of ideas. I know that meme has changed its name, but the classical name for meme, of this sort of individual building block of thought, that's much closer to that idea than the modern idea, than the modern word. But it's the things which people put together so that they can formulate it. So they've selected a specification out of a whole bunch of other specifications, and they've built up their idea of what they want. But they could have built up a whole bunch of other ideas using the same parts. And so what we're trying to do is find out what those parts are. This is what I said a moment ago. What needs to be true for the specification even to mean anything at all? So it's that underlying thing. It's the thing which couldn't change no matter how his problem changes. The internal language used by the stakeholders, when they start talking to each other and they're using their own domain-specific jargon, then they're starting to use that, they're using that problem space. It's going to inform the architectural foundation, but it's also going to define it, it's going to delineate it. It means that when we start constructing this problem space, we're saying this is the range in which the problem can be. And it can be anywhere in here and we'll deal with it. But if it strays outside, it's no longer our problem. So if we do want to try and defeat the evil Quark Empire, actually, we've got to go and build a new system to do that. So it's not only exploring, it's not only permitting this variability, it's defining it, it's limiting it as well. And in a moment, I'll show you why. Any questions at that point?
So the architect needs to have quite a strong domain knowledge, is it?
Well, that's a good point. The architect does need a domain knowledge. The stakeholders are going to be the ultimate parties. They're the people who really have the domain knowledge. To a first approximation, they have no computer knowledge. The developers and even the team leaders, they don't actually need to have a great deal of domain knowledge. Their knowledge is all concentrated towards the development, towards the computer. So the architect, his job is to stand in the middle and to speak from one side to the other. Now, he needs to be able to do that. He needs to understand the domain well enough to do that. And he also needs to understand the computer aspects well enough to do that. But actually, he doesn't need to be highly expert in either, because, as you'll see, he can validate that he knows enough. He doesn't need to be the expert, but he does need to be able to carry on the dialogue. I'm sorry, you had something? Yes, sorry.
Yeah, is it something to do with PM or similar to domain-driven design and ubiquitous language and your internal language? Is it similar concept?
I'm really glad you asked me that. No.
Okay.
But I'm going to tell you later on why it's not.
Okay.
And in fact, it's annoyed me because I've had to change my language because he pinched my words. So I was talking about a ubiquitous language and I had to drop that and put it into pervasive language. So let's talk about the pervasive language. Sorry, did I hear? Okay. Now, this problem space, you saw how much difficulty I had explaining it. I mean, once you've seen it, it's a fairly simple idea, but it's really hard to explain what it is. It's certainly nothing something which you can define formally, descriptively. But we can come close to it. We can come close to it using a pervasive language. Now, the pervasive language, and this is why it's different from domain-driven design, the pervasive language is the language which we're going to use to express the specifications. Now, there are a number of properties of this language that it has to have. First of all, it has to be very domain-specific, and it has to be able to express the specification in its entirety, entirely inside the bounds of the language. So when you say to your customer, well, he says, well, I want this, and you go, okay, is that what you meant? He needs to say, yeah. And then when he comes along and wants to change, he needs to be able to go, not like that, like that. So what's happened is your dialogue is now taking place in this pervasive language. You're no longer doing your dialogue in his jargon because you can't reach his jargon. He's the expert in that, not you. You haven't forced him into computer language, which is what domain-driven design does. What you've done is you've met him halfway in this pervasive language, which is designed to conduct dialogue. Now, I want to give you some examples of pervasive languages because you know what they are. You've seen them lots of times. And if I give you these examples, then you'll understand what they have in common and how to engineer them. Domains which are very specific, but which have lasted for a very long time, are things that we should be looking at because those languages have persisted. So those are the ones, those are successful by their nature. Number one, musical notation. How many musicians have we got? Oh, that's surprising. Okay. There's normally it's about half the hands go up. Now, the thing about musical notation is that you can pick up a piece of score for pretty much any type of music, and so long as you're a musician of some style, you can read it. A jazz musician can read a classical score, a classical musician can read a set of changes. Okay? It describes what's important about music. It describes simultaneity, and it describes the passage of time, and it describes pitch. It describes a whole bunch of interesting relationships. It is inherently spatial. It's designed to be written on. I mean, if you ever see a score that somebody has actually used, it's covered in notations. Another thing about musical notation is that it's extensible. It's naturally extensible. So people will write words on, they'll write symbols on. If you look at drum music, then drumming music, it's still on a staff, but instead of having little blobs, it's got crosses. There was a piece, I think it was John Cage who did this, where he was famous for doing the 273 seconds of silence and calling it music. But he did another piece, which was somebody climbing all over a grand piano, shaking a bunch of keys. And so he expressed this in this same musical notation. It was like a picture of a piano and people shaking stick figures, but it was still written on a staff. Point is, musical notation is a superb pervasive language because it not only describes music, it not only allows you to speak about music, it allows you to speak about music with whom you share with people with whom you share no other language at all. I can look at scores written by Russians and I can read them, okay? But it does something else. It limits our understanding of what music itself is. Now, Western music is based on comparatively simple rhythms. It's based on more or less complex harmonies. More modern music that came from through jazz and from the African music, that's rhythmically more complicated. So what we do is we use shorthands to represent that complexity. But I saw a thing on the telly about a percussionist who was really interested in Balinese drumming. Balinese drumming was supposed to be the best in the world. And she really wanted to understand it. And this program described her process, going and meeting these drummers and learning about their art and listening to them. And at the end of the program, she sat down and listened to him. And it was just clatter. It was meaningless. Because her Western ears, she just couldn't understand the grammar and the assumptions behind the music that was going on. And it was because the Western concept of music and the way it was notated, that in itself had constrained her perception of what music can be. Now, there is a central message of semiotics. Semiotics is the study of signs, and I commend it to all of you because we use signs and symbols all the time in programming. But the central message is this: if you don't have a word for something, or you don't have an internal representation for something, you can't even see it. Now, the Eskimos 20 different words for snow. That's apocryphal, it's not true. But talk to artists. Listen to artists speaking about colour. They will talk about the difference between cobalt and ultramarine. And, you know, you see blue, they see this distinction, and they can never not see it because it's part of their perception of the world. And they have this utilitarian language to express that perception. And it's important to them because these colours are not just what you see, but they have to react with other colours when you start mixing them together. There's a huge amount of knowledge attached to these names. And most of us in this room wouldn't even be able to see it. Okay? So the names and the symbols that you have available define your ability to see things. Your pervasive language defines your ability to conceive change, which is great. It means you can now absolutely predict what changes you're being asked for because they're only the things that can be expressed in this pervasive language. Does that make sense? All right, let me give you another example of a pervasive language. Circuit diagrams, electronic circuit diagrams. You've all seen them? Any electronic engineers here? Okay, right. Now, these things also have a grammar of their own. Generally speaking, I mean, electronic circuits, they need power going around them. That's what circuit means. But generally speaking, that's not how we think about electronics. That's just a given. So what you see is these rails, these horizontal rails carrying the power, and then all the circuitry is strung in between. And generally speaking, signal travels from left to right between these rails. And occasionally they'll have feedback in it. You'll take a wire out and it'll come all the way back. And this feedback is so significant that it's actually brought outside these tram lines and brought back in so that you can really see that the feedback is going on. And generally speaking, you'll have bits divided into areas, so you can say this is a functional block. Lots of interesting components. You know, the different devices all have these little different symbols. If we want to make new symbols, it's very easy. You look at circuit diagrams in the 50s, they had valves in, then transistors appeared, and then we have more and more exotic devices, and now it's these square boxes. But the thing is that the basic grammar, the basic notation survived, even though the vocabulary is changing dramatically. Again, what's interesting about this is that the Western approach to electronic design is this very high-level, top-down, deconstructivist approach, which leads to these kinds of pictures. Now, I used to work with a Japanese electronics company, and their approach is very different. Their approach is much more evolutionary, and they tend not to have these views, these sort of functional decompositions. And when you look at the circuit diagrams that they write, they have the same grammar, the symbols mean the same things, the connections mean the same things, and they are utterly incomprehensible to Westerners, because they're just built the wrong way around. It's like all the words are in the wrong order. And the funny thing is that they can't read our diagrams either, because it looks to them as if everything's been separated out. You've got 30 boxes instead of just one, and they can't see how the whole system fits together unless it's all pulled together. So then, again, you've got this example of this cultural distinction overlaid on the same pervasive languages. So you can see, if you can find a pervasive language with which you can express your specifications, then first of all, you've got a very clear dialogue with your customer. You can know that what he has said is what you've heard. Instead of having all of these functional descriptions in English, which nobody understands, half of it is written in a jargon which you don't understand, what you've now got is very clear diagrams which express exactly what he wants and allows him to change his mind. But you've also got a grammar going on there. You've got an expression of the things that make up his expression of the problem. But that's what we asked for. That is the problem space, this atomic structure, the things that you need to have in order to make the specification make sense. In music, you need to have a concept of simultaneity and pitch. In electronics, you need to have this sense of voltage and current and transformation of those. Whatever it is you're dealing with, you have to have these fundamental atomic units of thought. And what we've done by creating this pervasive language is we've brought it out and made them explicit. And this is so explicit that we can put these at the heart of our architecture. Now, I'm going to address your point about domain-driven design because this is the important thing. In all my days, I have never once done an exercise like this and come up with anything remotely resembling objects. Not once. The more time I spend doing this, the more I reach the conclusion that objects is a terrible way to analyze software. Because it doesn't represent anything in the real world. It's a purely programmatic concept. It's great for organizing software, but we're not trying to organize software, we're trying to organize solutions. And our solutions, or the problems that we're trying to solve, are invariably expressed in a language which is not objects. Now, what domain-driven design does is it says, this is how to find a vocabulary of nouns, what type of objects they are, and how to elicit them from the problem domain. But in doing that, he's already applying a transformational process. He's already saying, but they're nouns, they're things. But in almost every case, almost never is that really true. And I'll show you why. Consider the musical notation again. I say, what is the most fundamental building block in music? And you're going to tell me, it's a note. One of them. Okay. Let's think about that as an object. What does it do? Because objects are nouns that verb, right? They're things that do something. So what does that do? Does it play? Oh, because we don't have a pitch. For that, it needs a staff, it needs somewhere to sit, and it needs something to identify its pitch over and above itself. Okay, what about its duration? Well, or what about its time? Well, we don't even know its duration. We know that it might be a quarter note, but we don't know what its course really was, not until we've seen something else somewhere else in the script. Again, a large part of music is simultaneity, or if not simultaneity, at least association in time. What's it associated with? Now we've got to start putting other notes in. And it turns out that when you start analysing out music, there is nothing of value to be known about a note apart from its mere existence. And everything else that has any value in music is the relationship between these things and other things. And yet that goes completely against the grain, this concept of relationships. We know how difficult it is to represent relationships in object terms because we have the object-relational mismatch, which comes about precisely because we've got two things which look identical, and yet we can't put them together. So, the problem with domain-driven design is that it's stepping into objects far too early. It's trying to say the pervasive language is an object-based language. No, the pervasive language should be drawn from the domain, and it should be using the domain's relationships and the domain, what is important to the domain, not what's important to you. You don't matter here. We're still trying to talk to the client. Now, it was you who asked the question. Are you happy with that answer?
Yeah.
Okay, good. Would anybody else like to amplify on that?
A question. I don't see pervasive language helping on people coming from different expertise domains, like an architect or a domain expert.
Yeah.
because still they are not going to be talking that language. I think it helps to, I mean, for example, if you put between people working at the same level, two musicians or two engineers, electronic engineers, but you're not going to present, I mean, when a prince in the Middle East asks for an opera, the musician wasn't going to present him the scripts with the notes and the pentagrams, so they will sign some contract or something, but the partiture was including the contract itself, or was not the way to communicate between both of them. So still don't get the point.
Okay, the point is this, that if you can create a pervasive language, and you do have to create it, and part of what I'm going to be teaching is the process by which you do that. When you create that language, and if your client buys in, then what you've now got is a language with which to conduct a dialogue. Now, one of the things that we like to do as programmers is we like to decompose things. I mean, when I was at college 30 years ago, they told me no procedure longer than 12 lines. And we still teach that in various different forms. But actually, when people start drawing maps, they can be as large and as complex as you like, because what they do is they allow you to zoom in. You look at play scripts, for example, they're quite big things, but producers just flick through them and they get a sense of the pace. And then the actor's getting closer, they go, oh, this is my line, and then they go, this is where I need to be. Different people are using it in different ways. But what you have is a single map representing the entire problem. Now, you mentioned the example of an opera, but different people look at operas in different ways. The composer will have sketches, just very rough sketches, and he might do a whole opera on 10 or 20 pieces of paper. A conductor has an orchestral score, which is this big and has millions of lines. And you can't see them through a microscope because the conductor is just sort of looking at the shape and is turning the page. And then each of the musicians has a score which is attuned to them. But nevertheless, and it's one of the things about pervasive languages, there might not be only one. You might need more than one in order to cover the ground. But the thing is that you end up with one picture representing the entire problem. And so I think that part of your objection is scale, but actually people aren't frightened of scale. As they get closer to it and as they discuss the problem in more detail, they will simply put more detail into the map. It's only us who are frightened of scale, and this is us imposing our view on our clients, which again, we shouldn't be doing. Are you happy with that answer? Okay. So let's review what this pervasive language is. If we look at examples of these pervasive languages, these domain-specific languages, we see that there are certain things that they all have in common. The first is they are invariably spatial languages. They're drawings, without exception. They're not text. They're certainly not indented text. And the funny thing is that even in very odd places where you wouldn't expect to see it, like legislation, for example, legislation in most countries is laid out spatially. So there will be like what we would call conjunctions and disjunctions. They'll say, well, introduction, here's what this is about. And then in this condition, when this is true, and this is true, and this is true, and this is true, then this happens, and this happens, and this happens, and this happens. And the whole structure of the page is laid out to express these interrelationships. And so you can actually step back and you can look at a law and you can go, right, you know, there are some very large laws. I mean, there's an English law called the Consumer Credit Act, which runs to something like 800 pages. And yet, it's really easy to find your way around it because you just click through it. That's what I want. Okay? Same with very large circuit diagrams. You know where you are because you step back and you go, it's there. And you have this sense of moving forwards and backwards through it. So this visualness, this spatialness is very important. And again, tomorrow what we'll be talking about is how to design those languages, what the space actually represents over and above what the notation represents. Because what you find in these languages is the most important concepts aren't written down at all. It's the blank spaces which represent the most important things. Okay, the second thing is that they are highly domain specific. It would be utterly meaningless to write a musical score and put electronic symbols onto it. In fact, it's more than this. This domain specificity extends to, it, there's a word for this, and I've lost the word, I'm sorry. It's a vernacular. So you can use musical symbols and you can present them in a way which is musically meaningless, and everybody says, yeah, I know what that means. So wavy staves and a few dots on it, and everybody goes, yeah, I know what that means music. And then electronic symbols, they're so characteristic that you throw in a few electronic symbols and people go, yeah, I get that, that's techie. Even though electronically it means nothing at all. So these vernaculars are so strong that the languages themselves tell you what their domain is, even when the utterances themselves are completely meaningless. So that's another reason why we use visual languages for this, because no other style of language will do this. Sorry. Okay. They are highly expressive and they're multi-layered. This is something which, again, as developers, we're really bad at. Although we decompose and we look at things at different scales, at every scale they do the same thing. So if you're looking at a class which has got inclusions in it, you don't know if this is a tiny, tiny class which is used 100 million times, or if it's the app. Not until you start drilling into it. The shape itself doesn't tell you. But these visual languages, they're not like that at all. These visual languages, again, for the music, you can take one glance at a page and you know what type of music it is. Is it pop? Is it classical? Is it choral? What is it? Same with an electronic diagram. Even if you don't know electronics, you can take one look at it and you can say, that's a TV set. That's the high voltage electronics, and that's the power supply, and that's the tuner. And you can spot it instantly. And as you get closer, then you start to pick out the individual details within that framework. So that means that these are languages in which you can sketch overall strategies and then go back and fill in details later. And that too is a very important property of them. Textual languages, code, even things like UML don't do that. They are inherently extensible. If you find that your vocabulary is short, you can add new vocabulary. If you find even that your grammar is short, you can add new grammar. And I'll give you an example of this out of electronics. Normally in electronics, what you're dealing with is voltage and current. And so you have all of these different parts, and they're joined by wires, or they're joined by lines. And these lines represent wires through which current flows, and every bit of that wire is at the same voltage all the time. And this is the flow. This is electronics. It's electrons flowing through these wires in the circuit. That's what we're trying to represent. And yet, there's another way of coupling. You can get two things in contact with each other, even though they're not in contact. And that's done with magnetics. So you'll have a coil here, which you draw as a piece of wire, and you have a coil here, which you draw as a piece of wire. But now you want to understand that they're joined magnetically. So we actually draw a dotted line to represent this magnetic circuit. And sometimes you can have very complex magnetic circuits. And so you have, alongside this electronic depiction, you have this magnetic depiction as well. And the language lets you do this. Same with music. There are all sorts of very interesting pieces of musical notation where they've added things in which are not necessarily music. Who mentioned opera? Opera is a case in point where you're trying to describe action on the stage, where you're trying to describe emotion, where you've got the kind of thing that you'd find in a play script alongside the music. And so what they do is you've got this special notation which makes operatic scores instantly recognizable because they've added this extra stuff in. The point is, not that people do this, but that the language permits it. And that is where the language has got its success from, because it does permit this sort of malleability. Okay, I mentioned the clarity of the subject. A musical score cannot be anything but a musical score. A circuit diagram cannot be anything other than a circuit diagram. An architectural diagram cannot be anything other than architecture, building. It's instantly recognizable, and it's instantly recognizable even to people who are not domain specialists. Because one of the things that it does is it encourages you, once you've got this, once you see this vernacular, once you start to recognize the vocabulary that it uses, you're automatically drawn into the domain. So we started off talking about an accounting system. So if somebody starts drawing what an accounting system should do, not he says it's an accounting system, he says, and that means this. And it means this is our flow through. And we have this concept of a routing slip. And you know, the root itself seems to have value. And suddenly all of this language starts pouring out onto the page. And he's telling you the fundamental building blocks in which he's thinking. So the clarity itself is what you need, because establishing that vernacular, establishing that clarity, it establishes not just the clarity of language, but with it, the clarity of thought that your client needs to know what to ask for, and that you need to know what to build. Does that make sense? Okay. And finally, the domain's restricted. The musical score is not a circuit diagram. It can't be, and it won't ever be.
Isn't that inherently contradictory that they're extensible and restricted?
No, it's not. But it's a fair enough point. It's extensible. It's restricted because it's restricted by domain. What the extensibility comes from is basically in two different places. It's extensible in vocabulary terms. So for the circuit diagram, when they wanted a transistor, they drew a picture of a transistor, and the existing notation would accept the transistor because it wasn't doing anything fundamentally different to what a valve would do. So in that sense, it's extensible. When you describe, there are some very odd types of music, like mute music. It's actually written on 7 lines, it's not written on 5. Have you ever seen it? Have you ever seen anybody play the lute? It's got like 30 strings and they're all over the place. And somebody once told me if you spend 20 years playing the lute, you spend 10 of them trying to achieve it. But that's written on 7 lines because there's something very odd about lute music, which means that 5 lines isn't quite enough. So in that sense, you can extend the vocabulary, you can extend the number of things that you can talk about. But you can also extend the grammatical relationships. So the example from the circuit diagram is that when we introduced those magnetic circuits, there were still circuits, they still represented these relationships. They still represented a flow of some kind, but they were very different flows, so we could add them in. But what that didn't do was detract from the fundamental grammar of what was already there. It was entirely consistent with what was there. But what we couldn't do with those pictures, what we couldn't do with the circuit diagrams, is introduce a concept of time, because they have none. We couldn't introduce a concept of pitch, because we have none, because they have none. And similarly, when you look at the music, you can't introduce a concept of codes, because you never hear codes, you never perform codes. It's just not part of that grammar. So you're right, in a sense, there's a contradiction here, but on the other hand, this is what we're striving for. We've got the plasticity to be able to adapt no matter what he throws at us. And also that plasticity allows us to extend our architecture. But at the same time, it's limiting. It says this far and no further. And it does so without being restricted because it limits your ability to think. It's not a no entry sign. You can't think outside that box. The examples that I'm coming up with, like using the accounting system to defeat quads, they sound ridiculous because they are. And so what we need to do is when we find these pervasive languages, these expressions which don't make sense, just are ridiculous. And so nobody even goes into that space. Are you comfortable with that answer?
Yeah.
Okay.
I've got a question.
Sorry, where was that?
Yeah.
Yes.
So you're talking about some sort of intermediate ground where the developer and the sort of business end user can meet to sort of scope out the problem space.
Yes.
But, so to take your example of the accounting system, if my business user says the word credit to me, what if I, as a developer, don't end up, he doesn't use that word, he writes it down. Maybe he draws a picture of a banknote or something with an arrow going to a box or something, but I've still got to understand what he means. So there's still a limitation that we still, certainly you understand it, but pervasive language has got to be understood by both parties.
Yes.
Is it not? And what if it's not understood by the developer? Because this is a methodology to make us developers and architects better at future-proofing our solutions.
there's an awful lot in what you've just asked, and I'm glad you've asked it because it's a good question. First of all, you asked what happens if you write the word credits. Well, then slap him, because he's not in a pervasive language. He's writing, and we don't trust English. And you understand why we don't trust English, because the word can mean anything, and probably even other accountants will disagree in detail on what the word means. So yes, you want him to draw it, not write it. The second thing is that iconography is not a language either. Just because he's drawn a banknote doesn't mean to say he's in a visual language. It just means he's being literal and concrete and depictive. And you don't even want concreteness necessarily. He's still not operating in a grammatical structure. Certainly he's not operating in any kind of linguistic structure. So again, you need to get out of that. So the next thing that you do is say credit. Well, why do we care about the credits? And so he's going to say, well, because when we get this credit, we need to put it somewhere. We can't just leave it lying around. It has to exist somewhere. Now, what's just happened here? He's told you that, first of all, he's thinking spatially about the accounts. Good, you want him to think spatially. And then he's talking about movement of things. This credit is now a thing and it's moving from place to place. So now we know that our language, deep in the heart of our language, is this concept of flow or of events. And so now we can start looking at precedent for that. We can look at things like railroad timetables, or we can look at shipping manifests, or all of these people who are used to dealing with moving things from one place to another, if that's what you elicit from that process. And then what happens is you go over and you say, okay, does this what we mean? And he goes, no, like this. And now you've got it, because now you're in the shared language. Now you've had a guess about what he means, you've tried to express that guess to him, and he has now confirmed that the language is right, but the expression is wrong. Got it. And that shared language, it's not entirely your responsibility. I mean, as I say, tomorrow what we're going to do is I'm going to talk about exactly how to construct these languages and how to validate them, because you do have to make sure that they're right. But what you end up with is something which doesn't belong to you, in the same way that UML or the code belongs to you. But the funny thing is, it doesn't belong to him either, because you're getting him out of his Java space, which is a space that you can't get into fairly. He's the expert in that. So you need him to come and meet you halfway. And so this visual language is it. So that was a long question you asked. It was a long answer I gave you. Are you comfortable with all that, or do you want to drill down some more? Okay. Anybody else want to say anything?
I just think the user, to use your examples, the music, the audience don't care about the score. To use the electronics one, the consumer doesn't care about the electronics diagrams. So, there's quite a difference between the end user or, maybe a domain expert if you were composing for an orchestra. But even there, there's quite a disconnect, I think, between the diagram and the ultimate consumer and user.
But we don't owe any responsibility to the end user. We owe our responsibility to the stakeholder or to the domain expert who's commissioning it. You're right that the musical score means nothing to the audience, but it means a hell of a lot to the musicians who are performing to that audience. And it's them who we're dealing with. That's the level of expertise that we need to be talking at. Now the thing is, if you have an idea for a musical piece and you walk in front of your orchestra and you say, okay, now, you ready guys? Da, 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 da. Just carry on, you're the experts. That's not enough. And it's not enough even for an audience. So you need a specialist language to communicate with other specialists. So that's what you're trying to create here. Does that make sense?
Well, they need to hear it, don't they? So it's a bit like
who needs to hear it?
The audience.
Yes.
To produce the music, you're in the same way that a UML diagram might not mean anything to your stakeholder, but a prototype or a POC it might be more meaningful.
Absolutely, and I'm claiming here that one of these expressions, one of these pervasive language expressions, also should mean a lot to him. And if it doesn't mean a lot to him, then it's failed. But the complexity that's involved in some of these things means that the proof of concepts or the prototypes often fall very short. You can't use that as the basis of understanding the specification. You need a much richer sort of language. But to continue your analogy, the people who are applying for the loans don't care at all about how the loan gets applied. They don't care at all what accounts internally the bank uses. What they care about is, I want my money. The bank cares how they get the money, and the bank cares even more about how the bank gets it back. So, but at a very literal level, we just don't care about the users. What we're doing here is we're figuring out not what the user experience is, but how to deliver the user experience. In the same way that the musicians need the score, not the audience. In the same way that the engineers need the circuit diagram, not the people watching Neighbours. Are you happy with that? You're not, are you?
Okay, we'll move on.
Okay.
Yeah.
Yes.
Yeah, I have a question. So, when the customer come to us, so should we ask them to get the language first before we talk about the requirements? So, based on your example of accounts, so if the customer comes to us to require us account system, should we ask them to talk about the language to describe everything in the financial before about the system itself? So the customer won't put aside a lot of time before going to their problem.
Okay, so let me play back your question to make sure I've got this right. You're saying that to go to the client, invent this language, get a complete specification in this language before you do any work for him is onerous.
Yeah.
Okay. Yes, it is. But you don't have to do that. Because remember, one of the things that I said right at the beginning is that we want to validate these specifications at the earliest possible time. So what we want to be able to do is, first of all, evolve these things over time. It's not just a gift from the gods appearing in one massive session. You're going to take time over it, and you actually are going to evolve the language over time. So that's the first thing. But the second thing is that as you do, it needs to be animated, it needs to be testable. And it needs to be testable in informal terms, as part of the dialogue with the stakeholder. But it also needs to be testable in formal terms. In theory, you can actually write compilers to check these things and to make sure they're consistent. But what you would do is you would go to him and you say, okay, well, describe your problem to me. Look, we've got this requirement. What does that actually mean? Okay, it means that. No, it means that. Okay, but if it means that, then what about that? Oh, yeah, you're right. That happens a lot. Because they don't understand their problem as well as they think they do. So gradually, this thing takes shape, and more you can put more detail in. Now, you don't have to go very far down this line before you understand, you might not understand the specification, but you do understand the grammar. You start to understand the fundamentals of the language very quickly. So now, you can start coding. You still don't know what you're being asked to code, but you do know what you need to be able to deliver that code. You now have your architectural foundation. You now understand, at a very early stage, what you, in the same sense that what we're trying to find out is what needs to be true for this specification to make sense. By answering that question, and at the same rate at which you're answering it, you're also answering the question, well, what do we need to, what foundation do we need in order to deliver this specification, whatever it turns out to be? Does that make sense? So you're right, it is onerous, but it's only one of the dialogues that's going on. It is a dialogue, and it stays live throughout the problem. Remember, I said that change is the problem. We're actually trying to elicit change. We're not even trying to suppress it. We want him to get his red pen out. And we want him to say, no, I've changed my mind. This isn't making sense to us anymore. I actually want him to take this chart to other people and say, this is what we've decided. Now, come and validate it for us. And come back and say, actually, the higher ups have changed their mind. We can do a better job here. We want that because that's the emergence kicking in. So it's absolutely not about pre-preparing this. This is absolutely not a waterfall technique. It's about getting a meaningful dialogue. It's about getting a shared language. It's about making sure that you both mean the same thing. And by that, I mean from the business leaders, from the technology commissioners, your architects, right down to your code base. It's all got to mean the same thing. It's all got to be congruent. Because if you introduce cracks in it, cracks are where the faults develop. Okay? Right. Anybody else? Yes.
I think our place at the moment, this kind of stuff is good about business analysts. We tend to offer more business analysts. This kind of stuff is good about business analysts, consultants, our place.
Yes.
So the architects are sort of downstream from us, so we get Chinese visitors
Yeah.
going down from us.
Is that working for you?
So would you see the architects
Yes, in fact, I would say that using techniques like this, there isn't a distinction. Architecture and business analysis should be the same thing, because what you're trying to do is, as I just said just then, you're trying to understand the problem, understand the building blocks of the problem, and you're trying to get everybody corporate, you're trying to get everybody saying the same language. So if you start introducing Chinese walls and Chinese whispers, then by definition you're trying to separate them up, and that seems to me to be entirely perverse. Okay. Anybody else want to say something? Okay. Oh, you stupid machine. Okay, so let's sum up this language. It is absolutely drawn from the problem domain. And by that, I mean you cannot construct this without the domain specialist's active involvement. Agile says you need the product owner involved, or whatever it is, whatever the discipline called it this week. But you can't proceed without a stakeholder of some kind guiding you. I say you absolutely can't proceed with this language without the domain experts. They have to be there. They have to be complicit in making the language, because it's a shared property. It's not yours, it's not theirs, it's co-owned. It isn't the problem space, but it does indicate the problem space. Now, again, to use the musical analogy, the problem space is music. We know what we can hear, and actually we don't know what we can't hear, but we do understand the grammar of music. And what we do in musical notation is we try and write that down, but the experience of reading a score is not at all the same thing as listening to a performance. So this isn't the problem space, but it does point towards the problem space. And sometimes you need more than one expression, and tomorrow we'll be looking at examples of when and why you'd have that more than one expression. It is formalizable. We know, well, musicians know, what well-formed music looks like, and they know what meaningless music looks like. Electronics engineers know what a well-formed circuit diagram looks like, and they know what a meaningless circuit diagram looks like. You need to have that same concept. You need to have this sense of correct grammar. Because the thing about a correct grammar is that not only does it disambiguate things, it means that you have more than just a collection of nouns, but it means that you've got something testable. We use type now to verify the correctness of programs. And I don't know if anybody remembers the days before type. It was hell. Type was absolutely transformative. Now, what grammar is in these terms is the equivalent of type in programming terms. It says, this just doesn't make sense, so you've got this wrong. There's no way this can be right. You have to go back and revisit it. Now, there are programs which allow you to draw these shapes. There are projectional editors like, I've forgotten the name now, MPS. What was that? Yes, MPS. Which enable you to construct these pictures on the screen. And they are genuinely pictures on the screen. And implicit in this is a sense of correctness that lies behind it. So it won't even allow you to construct incorrect utterances, which gives you this extra check that you're doing the right thing. So, most of these languages we won't formalize. Most of these languages will never make it off the paper. And if the grammar is simple enough to be recognizable when it's wrong, that's all you need. But if it's formalizable, then it means we can formally check it. We can create tools to check it. If it's formalizable, we can create tools to animate it so that we can actually see what the consequences of this is. So it's like playing the music. What does it actually sound like? Right? Now, in order to do that, you need this formalizability. So you need more than just sort of general wavings at an account over here and an account over here, and some magic happens in between. You need to be more formal than that. So this formalizability lies at the heart of this discipline. Now, what are we going to do with it when we've got it? We're going to use it to construct the real specifications. We're going to write down, we're going to say to him, yes, we know we've got all of these things here, but can't build that. That's in English, and it's in this very specialist English. We'll build this. So this is the specification. It's going to change. We don't care. We want it to change, but it's still the specification. It's our best guess of what we want to build right now. An interesting thing about this is that it tells us what we want, and it also tells us the difference between what we want and all the other things that we might have wanted but don't. And that's an important thing to be able to say. The other thing is the difference between what we've got and what we want. As a consultant, I learned this years ago. I would go into a client and they would describe their problem to me, and I wouldn't listen to a single word of it. And I'd say, okay, tell me what you want to be different. And suddenly I'd get a completely different response. Now the fact that that you're able to use this notation to say, this is what we've got and this is what we want, that enables you to use this notation to say, well, this is how we get from here to there. And 9 times out of 10, the hardest part of your job is the migration, not the building itself. So that's why we're using this to construct the specifications. And again, it allows us to predict the range of plasticity, the range of movability that we can expect in the test.
That's a good question.
Yes, sir.
Do you create a separate language for each system you're working with?
Yes.
Or are there commonalities between them?
There are commonalities, and what you will find is that you'll see the same kind of ideas over and over again. So if you're doing one accounting system, say, then you'll find that other accounting systems will look similar. But what you want to avoid doing is imposing a prejudice on somebody. So if you go along and you say, well, I've just been on a job and this is how they did it, so this is how you're going to do it. They say, no, this is how we do it. So you have to be prepared to respond to that.
But so for each system you're going to design pictograms or whatever to describe the entities, the objects, the things you're dealing with, and the elements that describe them. So it's going to be a completely visual thing.
It is absolutely visual.
Yeah.
It's important to understand what the most important concepts are, because those are the things that they're speaking about. And as I say, in most notations, that's what the white space represents. So you have to elicit that at a very early stage. But again, part of what we'll do tomorrow is I'll show you how to design those languages, and I'll show you how to find precedent that you can work from. You very, very rarely need to start from scratch, but you do need to be open-minded as well, and allow them into it. Is that an adequate answer to your question?
Super.
Okay. We're going to use this to direct the development. What will happen when you create this language is, as I say, we don't care what the specification is, we care only that there is one. Because in the early stage of the development, when you're building the architecture, what you're building is the foundation on which you're going to build the solution. So what shape should that foundation take? Well, it's the language that tells you, not the specification. The language will tell you what are the really big ideas, the things which are so big as not even to need saying. And then it will tell you, and what are the units of thought that exist within that space. And those things are the things that you start off by implementing. So at the very early stage, as you're starting to create the specification, as you're starting to deliver it, as you're starting to firm it up, then you're also creating your architectural foundation. So this actually, the language itself, not the specification, is what drives your development right at those early stages. Does that make sense? Okay. As I say, we care very much about change. We want him to change his mind. If he changes his mind, it means we're doing our job right. He fixes number 1 problem, number 2 gets a promotion. We fix that, number 3 gets a promotion. And pretty soon, he's trying to find problems to throw at you because he hasn't got any problems left. What a wonderful world that would be. But if we actually go to him and he say, are you sure you want this? Because we could give you that. Why don't you take it to your boss? Do you remember that crisis that happened last year? Remember that problem that you had? How would this fix it? So all the time, you're saying, you know, here's the real world situation, here's the world you live in, here are the problems that you're solving now. There's the picture shown. Because you now have a shared language, which you both trust. So he knows that when he gives you these explanations of these highly technical things from his domain, because these are the things that have blindsided them in the past, he has the confidence that you will understand the explanations. Okay? And then finally, you use this to limit the mission creep. It means he can't try and defeat the evil Cog Empire. It means he can't start putting in things that aren't properly part of the problem space. And in fact, one of the things that happens is you get a sense of the problem space itself. It becomes a thing in your own mind. It's not something that you ever show to the client, but you get a sense of its scale. And what happens is, as you start understanding what the building blocks, what the intellectual building blocks are, and you start developing them, you find you develop less than 10% of it. Because that's what you need. Because you're only ever developing the bits, which are delivering value to the customer. Because there's nothing wrong with Agile, it's a good way of working. So we do need to be selective about what we make. But so we only build about 10% of what this pervasive language is suggesting. And then he comes up with a bit more. You know, he changes his requirements. It basically boils down to reconfiguration. You don't have to do major reprogramming. It's just because you've already got a foundation. You've already got a toolkit for solving these problems. And then he says, yes, but. And he introduces a new noun, or he introduces a new relationship. Okay, that's fine. So we'll extend our problem space, we'll put a new concept in, we'll develop that. When you start getting up to 50% capacity, you know your system is starting to reach the end of its life. When you're up to 80% capacity, there's nowhere else to go. And so now is the time when you need to be thinking about end-of-life, decommissioning, building up the next one. So you always know, first of all, we can limit the mission creep, and then secondly, we know when the system's over, and we know when it's time to retire it. And we've got plenty of warning. We can even predict to within months when the old system is going to fall over. And of course, that's the other thing. As an architect, you need to understand the lifetime. I was talking about, is it 5 years, is it 10 years, is it 30 years? But actually, you need to know. And this is a tool that will tell you. Any questions at that point? Okay, so after all that, you came to a talk about problem space analysis, and I've hardly used the words at all. So let me tell you what problem space analysis is. It's a process. It's the process of eliciting this pervasive language, and more to the point of validating it, of making sure that it's a correct expression, and it's a complete expression, and it's an unambiguous expression of what you want. It's the process of creating the specifications using this pervasive language. Because ultimately, it's a collection of specifications, or it's a system which answers a collection of specifications, which is what you're going to deliver, and that's what you're going to be assessed on. So, the problem space analysis is the process of creating those specifications. It's the process of actually building a system based on those specifications. It's the process of designing the architectures, because this is absolutely an architectural technique. It's the software designs, it's the stories. This problem space, this pervasive language, should inform and influence every single step of the development process. And then finally, it's the process of building real solutions, using Agile if you want, or using other techniques if you've got constraints which prevent you from using Agile. But it's the process of actually constructing, testing, accepting, and delivering that software. The actual, fulfilling the contract which you signed in the first place. So, you can see why you had to wait to the end for the answer. But I'm done, we've got 10 minutes left. Is there anything that you'd like to ask now?
Could you show us an example, please?
I haven't brought any with me. That's really what tomorrow's about. Tomorrow we're going to do some worked examples. We're going to go into some of these in a lot more detail. But tomorrow is specifically about doing this and about the validation. The slides are all on the app, by the way. I mean, I'm not saying don't photograph, but they're available in the app. Yes?
Just wondering, how would you know that you're actually asking the correct questions if, for example, if you're a developer, if you're not, it almost feels like I've had people where we have sort of technical analysts or business analysts or maybe even PMs sit down and have like a facilitative workshop with the clients. So is it more for them to be doing that, or should the developers also be involved in that phase?
I think it depends on the way your business works, and it depends on the scale of the project. You cannot make 100 developers all domain specialists. It's a terrible use of time, and they probably won't manage it anyway. So we're trying to avoid doing that. But at the same time, what we can't do is allow the programmers to operate in a completely different space, in a completely different intellectual space, to to what everybody else is trying to deliver. So we need some way of joining them up. Now, I keep on using the word architect, and over here he was talking about the distinction between an architect and a business analyst. But I think that these roles, part of what I'm trying to do here is I'm trying to blur these boundaries. We cannot step into the domain specialist world and expect to be as specialised as they are. And we cannot expect them to step into ours and validate a piece of UML, for example. But similarly, they are not going to be checking each individual bit of code. So I think that part of what's going to happen is that once you've created this pervasive language, once you've deconstructed it and analysed it, then you now have some sense of what it is you're trying to build, of the foundations. But you then need to go through another stage. You need to start saying, well, how actually are we going to implement these? And I know I've bad-mouthed objects pretty good, but ultimately, we're going to be doing this in object-based languages. So somebody has got to take these ideas, they've got to take this analysis, and they've got to turn it into something that can actually be constructed by programmers. And they've got to turn it into a set of tests by which you know that you're delivering the right thing. So that seems to me to be a second phase of analysis. Ultimately, it's going to reach the programmers, and it's going to reach the programmers in the extreme case, in very, very programmatic terms, no longer in the problem-based terms. But so long as the terms, so long as the basic ideas in the pervasive language extend down, and they're still present at that object decomposition, then it's succeeding. The fault would come about if at some point you break the chain, and you're talking about accounts over there, and now over here, you've lost the accounts, and now you're really talking about tables. That would be a failure. So we need to be able to get to the programmers still talking about an account, even if the account is expressed as a SQL create. Does that answer the question that you're asking? Not quite.
Sort of. For example, if I'm the only developer on a project and it's just I need to be the person, so is it more of a I take on that hat, put on that hat, and ask those questions and
if you are the only developer on the project, elbow people out of the way, get there, be part of that creation. Because we want the least amount of Chinese whispers that we can possibly get away with. When you're working at scale, you've got to accept the overheads and the costs and the difficulties of working at scale. If you're the only developer, you don't have to accept those. Get in there, do the work, talk to the client, and build up that personal relationship, which is the other thing that you need, of course, in order to make the work successful. You comfortable with that? Yeah. Okay. Any more questions I can answer? Yes, sir.
Yeah, my scepticism is around, because it seems that to do this, you've got to really get out of your comfort zone quite a lot, both the stakeholder and yourself, because, and where I'd be sceptical is you get the stakeholder in the room and he or she is immediately just going to start talking jargon. So this the challenge is to get them to stop talking jargon and to get into this middle ground. And so the theory aside, what I would find the most challenging aspect, assuming I fully understood how to do this, would be, well, how do I now get this person to stop talking without me also looking like a complete idiot in the room, because he's going to be thinking, why are you asking me, why are you asking all these questions, and he's busy, he's coming, he's only got a certain amount of time. It seems like there's a lot of kind of people skills required here, a lot of psychology is required, because you've got to get this person into this space,
yes, you do,
to make this work, and I just don't know how you would do that.
Okay. Again, there are several suppositions in your question. The first is he's too busy. If he's too busy to be part of your team, then you haven't got a team. You cannot do this without him. He is not prepared to brief you, you haven't got a brief. If you say to him, look, got a day, I need you for a month, even if it's only 2 hours a day for a month. And he says, no, I'm too busy, just do it. You say, so fine, anything I write, you pay me for. This is the specification, I'd like you to take, yeah, just put your signature at the bottom, I'll put in detail later. By God, you'll have their attention. The second thing is, he's going to start speaking jargon, but he knows he's a specialist, and he is the big I am. I have never yet met anybody who doesn't love talking about themselves and their own expertise. Never once. And so if you say, in words amounting to, please slow down, I'm not as clever as you, I love to hear you smart people speak. Now, let me just make sure I understand what you say. He will join your level, I guarantee it. And it's extraordinary the extent to which you can lead people. I used to teach people how not to answer questions, and it's actually really hard. Have you got time, by the way? How are you doing for time? Thank you. See? How long did I have to wait? A second? It's a stare-out contest. But you only have to stare him out for a second. So, once he joins you in space, if he's not prepared to join you in space, you can't work with him. And I admit, you get arseholes. Don't work with arseholes. But most people will be happy to join you because they actually want to speak about themselves. And they also want the solution. Generally speaking, you will go into a situation and you might find a lot of antipathy. They might have worked with development companies before and they might know that they will never get what they want. So they all speak a different language and they're all just aliens. They might already come in with those preconceptions. But if you say, look, I don't understand, help me to understand, it becomes a collaborative effort and it becomes a shared space. And it's an extremely constructive place to be. And particularly if you reassure them this is not contractual. And more than that, the best I can say is try it. Come along tomorrow, let me show you the technique. Fight me if you want, tomorrow's your chance to challenge. But at the end of the day, you'll have a lot of the skills that you'll need to do this. Are you comfortable with that, or do you need to say more?
Yeah, no, I really wanted to know what your answer would be.
Okay.
It's quite a difficult question. I'm satisfied.
All right, fine. Anybody else?
What is this acronym MPSE again, please?
Meta Programming System. It's put out by JetBrains. It was something that was that Martin Fowler's quite big on. But basically, it's a compiler language construction workbench. But it's not just parsers. You get like editors, quite sophisticated editors, for free. And part of the idea is that it will merge different kinds of languages together in all sorts of interesting ways. It's worth looking at. It's a terrific tool. Okay, any more?
Do you take notes or something, documentation out of the written documentation after these discussions with the domain expert somehow?
Sorry, that's me here.
So do you take some documentation? Do
Yes.
you make some documentation?
What I tend to do is I tend to get a flip chart pad and put it on the table. In no chairs. It's a standard meeting.
Yeah.
And I will put pens, but not marker pens. I'll use barrows and just leave them on the table. And people will start picking things up. Sometimes people use pens, sometimes people use pencils. But what you don't want to do is draw great big things. Think that they're on the flip charts. What you need is a big expanse of paper for the detail. And I would say there, you pin it on the wall. I think it's, people have like the Kanban boards on the wall, they have the task plans on the wall. I think there is no better, if you only have one thing on the wall, it should be this. Because it establishes what everybody's trying to build, it establishes where you are, and people will go up and have discussions, and it'll pick up fingerprints. And every now and then, you might have to redraw it, but it's your major planning tool, it's your major communication tool. So yes, the output of this is absolutely this piece of paper. Sometimes you need a very large piece of paper indeed, sometimes flip charts aren't big enough. But what's interesting is they do all tend to do on one piece, you just need a big enough piece of paper. If you find you're starting to say, go off page, and not start taking pages together, then actually it's often a sign that the language has failed and you need to go back and revisit it. It's a sign that you're decomposing too soon. And that's That's what we do. We like to decompose much more than anybody else does. Is that answering your question? Okay. Well, if there are no more questions, this is your last chance to get that delightful coffee. So, if you're driving a car and everything's working fine, and then suddenly, and it's all over the road, this has happened. The car is now malfunctioning. It's not steering properly, or it's not going properly, or whatever it is. But it's malfunctioning, and you know it's malfunctioning because it's not doing what you wanted to do. It's not steering along the road, or it's not accelerating properly. So you are understanding the fault in terms of its failure to function. But somewhere else, there is the explanation of that. So there's a linkage broken, or there's a pipe come off, or something like that. That's the defect which has given rise to the malfunction. And this almost always is a fault, it's a break, it's a fracture in a vehicle. Now in software, things don't break. If we've got defects, then they're there because somebody put them there. But you still have this separation between a malfunction and a defect. The malfunction is how you know it's gone wrong, and the defect is the cause of that malfunction. Now you can't have a malfunction without a defect, but you can have lots of defects without malfunctions. You know this. You know that you can write your code and you test it and it's fine and you put it into production and suddenly it's crashing and burning all over the place. It's malfunctioning like hell, and you can trace it back to a defect that was there all along. But it hadn't caused a malfunction until you released. Now let's look at the cost of this. Let's suppose we introduce the defect at the coding stage. And you'll see various versions of this picture, by the way. You'll see different multiplication factors, you'll see different stage names. It doesn't matter. The basic story that this picture is telling you is absolutely consistent and has been replicated many times over. So, you introduce the defect, you discover the malfunction, you try and recover the defect, it costs you an hour, that's $25, something like that. So, it's a nice, simple, easy fix. But let's suppose you don't find it though. Let's suppose you throw it over the wall to test, and they have to find it. And so now, they're doing the test, and they find it, and they write a report, and they hand it back to you, and you've got to stop what you're doing, and now you've got to find the defect, and you fix it, but now you fix it. Now that costs you maybe 5 times as much. Okay? Let's suppose they miss it. Let's suppose you get it into production, or you put it out in the wild, and it's your customers who find it. Now, that's very much more expensive. Now you've got to go all the way back to the coding, and you've got to try and fix it at that level. And now, it's costing 125 times as much as when you started. And we all know this. The later you find the defect, the later you elicit the malfunction, the more expensive it becomes. No problem with that, right? But here's what's interesting. This is true right across the production chain, or right across your development chain. The earlier you introduce it, the later you find it, the more it costs. So if you get your architecture wrong, and you don't discover until you hand it out to the customers, boy, are you in trouble. And if you get your requirements wrong, and you don't discover it until here, then this multiplier is generally of the order of the cost of the project itself. If you built the wrong thing, you not just do the problems change, but the whole language, your whole mental approach to the problems have changed as well. Now, when our specifications change, it's because we've got these new problems emerging. And that's the proof that we're solving the old ones correctly. Change is not a bad thing. Change is not only, the way Agile presents it, they say that change is the problem that we have to solve. No, change is evidence that we're solving it. The real problem is something even bigger, but the fact that it's changing is so important. We can't deny that, so we can't go back to pure waterfall. So, this is what we appear to be trying to do. We have this task that we're trying to solve, and we're always trying to catch up with it, and we're always like one step behind. And this is true either in a waterfall model, or in an agile model, or anything else. And it's the fact that that fly is a moving target. That's what stops us from being at all formal about our specifications or our architecture. So that, what you just saw, is the problem that we have to solve. Would you like to see my fly again? Because I spend ages on it. Okay, maybe not. Now, none of our existing methodologies address that problem correctly. Craftsmanship, this is the idea that you can get good at something by doing it over and over again, which you can. Ask a musician, ask a woodcarver. But what that does is it actually denies change, because the musician says, I'm going to perform this 100 times so that the 101st performance is perfect. The woodcarver goes over and over again so that it's perfect each time. So he's saying, I am trying to solve the same problem over and over again. How many people in this room have solved the same problem even twice? Enough said. Waterfall impedes change. You've got this plan, you're starting building to the plan, and somebody says, that's not exactly what I want. Okay, that's fine, we can cope with that. What you need to do is fill out this change document. You need to send it to him, he's going to photocopy it, he's going to send it to all these different people. They don't know what they're doing, so they're going to form committees to discuss them. It'll come back to you in 6 months' time. That's fine. So the whole process of waterfall is to impede the process of change. It's designed to do it. And it's why it doesn't work in software, but it's why it does work in something like avionics. Because in avionics, you want to be absolutely sure what you're building. But what about Agile? Agile suffers from the opposite problem. Agile is completely adrift on change. It's like a ship with no sail. It's just swept by the tide. And the fact is that every software project does actually have an aim in mind. We do know, somebody somewhere knows what we're aiming for. There's a business problem to be solved, there's costs to be met. I mean, you can't just completely let go and say, well, we'll go wherever the wind takes us, because that doesn't actually get you where you want to go. It gives you very nice meandering, it's tremendous fun to work in it. But in commercial terms, and even in terms of validation terms, if you're not bored after 2 years doing that, then you've got no brain. So what you need to do is, even with Agile, Agile is not addressing the change problem. Change it exists, but it's not our master. It's simply one aspect of the problem. Let me explain to you what you're about to see. I've done several workshops on problem space analysis here and at other shows, and I've taught it outside of the shows as well. But the trouble is that every time I've ever done it, it's been a really big thing. It's been a whole day, or it's been 2 days, or it's been a week. And I thought, well, I and the conference organisers thought, well, it might be quite nice to do an introduction just to explain to people what this is about, and to show you why you should be interested in this, and why you should come back tomorrow and do this all day. Come on in. Has anybody heard of this stuff before? Does anybody know what problem space analysis is? Okay, so why are you here? No, seriously, I'm curious. I mean, let me ask a more direct question. Who here would describe themselves as architects? Okay. Team leaders, project managers, and humble developers. Okay. Now, this computer has been playing ball. Okay. Now, those of you who are working with developers particularly, but architects as well, I want to ask you about the environment you work in. How many people are doing a process which is more agile? Even if it's only Scrum, which isn't agile, but... Okay. Now, I'm going to come back to you guys. Who is still doing waterfall or command and control or something like that? Nobody. Okay, so a lot of you aren't doing anything at all. Anybody doing any process that isn't either of those that you describe as distinct? Okay, what are you doing?
It's kind of vague in the middle. We work on tasks, right? But there's a team of kind of 5 or 6 of us, and people move between projects depending on what needs to be done. Effectively, we've got 2 different product managers deciding what to do, so they agree with themselves. It's agile-ish, but I wouldn't kind of agile.
Okay. Is it working for you?
Yeah, it does. I mean, when the product managers pressures change, hours change, but it does work. Get things done. We always got to work on.
Okay. Right, you guys who are doing agile, I've got a question for you. Those are the ones who put up their hands first. Is that working for you? I mean, the promise of agile, right, is that you can produce a lot of value very quickly, highly reliably. Are you doing that? Anybody?
Most of the time.
Really? Okay, one person. Now, this is funny because in the course of the work that I've done, I'm a contractor, so I've seen an awful lot of development. I've seen a lot of waterfall type development, and I've seen a lot of agile type development. I've seen a lot of projects fail, and I've seen a lot of projects succeed. And as far as I can tell, the difference between a successful project and an unsuccessful project is not how agile it is. In fact, that seems to have no relation to the outcome at all. The actual success factor, the real fairy dust that makes it work, is something else entirely, and it's completely independent of your methodology. Now, part of what problem space analysis is about is to try to understand what that is, and to try to characterize it. Has this worked? Good. Now, I'm going to shut the door now, because they're not here by now, it's too late. Now, there's something I want to talk about here, and that's horizon. Developers, particularly agile type developers, have a horizon of a couple of weeks. That's the size of the sprint. So you know what you're doing for the 2 weeks. Theoretically, you're not supposed to know what you're doing following them. Okay? If you're working on it as a team lead or a project lead, you've got a much longer horizon. You've got a sense of a business requirement that you have to bring in. It's not a tiny atom of value. It's not a minimum viable proposition. It's something rather larger than that. So generally speaking, the horizon there is six months to 2 years. Generally these days we're trying to get it shorter. We're trying to aim towards the 6 months. Okay? And then you have to look at architects. And you come to the architecture conference, everyone's arguing what's the difference between an architect and a developer and a team leader and just a boss. And this is the difference. It's the horizon. So what's an architect's horizon? 6 months? No, way more than that. 5 years, maybe 10 years. Sometimes 30 years. Those of you who can remember the Millennium Bug report, the whole point about the Millennium Bug was that we had got deeply embedded in all of our code bases that was 40 years old and written even before people could count up to 2000. So the thing about an architect is that he is trying to predict the future 30 years ahead, potentially. How can he possibly do that? The whole point about Agile is that, well, you can't trust the specifications because they don't change the specifications before the ink's dry. And yet, we've got architects who are trying to predict 30 years ahead. How is that even possible? And it is, because you can tell the difference between a good architect and a bad one. So, this fairy dust, this thing which makes the success factor, this is the thing which the good architects do, and the bad architects don't. And actually, the developers are not looking at because they've still only got this 2-week horizon. So that is what problem space analysis is all about. Now, again, before I get into the meat of it, I want to show you. I would like to talk a bit about reliability. I care very much about reliability. If you've been to any of my other talks, you'll know how much I care. But you often see pictures like this. What we've got here is a sense of how much it costs to fix a defect. So you've introduced a defect at one point, and then it's malfunctioned at some other point, which is the point at which you're going to fix it. Do you understand the difference between a defect and a malfunction? Anybody not clear? Okay, thank you. That gives me an excuse to explain. Imperiled the whole project. Now, just to make it clear, this is a logarithmic scale. What this chart actually looks like is this, and that is going up and interfering with the flight path out of Heathrow. So that's why this buggers up your project. Now, look at this. We all test our code as we're writing it. And we test it furiously. We have regression testing, we have integration testing, and then we toss it over the wall to a test department who are testing it. We care about this, and we care about these costs. But if we had any brains, we would be testing our architecture, and we would be testing our requirements with the same, if not more, assiduity as we test our code, because this is where the real damage is done. And yet we don't. And the reason why we don't is that by the time we get to code, we've now got something formalized, something testable, something that you can run. And it's the first time at which we've got it. There's a sense in which this is the first moment at which we can test. And if we try to test it, how can you test an architecture? It's a load of pictures on a wall and people with long hair waving their arms around. And as for the requirements, well, it doesn't make any sense at all. And yet, all the risk is over here. So, is there some way in which we can figure out what these, where we can look at our architecture, where we can look at our requirements, and we can say, yes, this is actually what we want to build, in spite of the fact that we're operating in a world of change. If we can do that, then we can get a very high degree of safety right the way through the rest of the development. And we can get the promise that, that architecture really, we can deliver the promise that architecture claims to be able to deliver. Does that make sense? Now, I know I haven't told you yet how to do it, but you understand the argument. Does anybody want to challenge me on this? Okay, good. But this is our problem. Change is a fact of life. The whole principle behind trying to write a specification, it says, this is what we're going to build, and this is what we're going to test against at the end, and if they don't match, then we've got it wrong. And yet, we know that specifications change. Actually, there's a very good reason why specifications change. It's in the nature of software itself. What happens is, when you start working on a problem, what you tend to do when you're writing a program, you're trying to take a manual process of some kind and you're trying to automate it. This, ultimately, all programming boils down to that. You're trying to automate something. And that means that having taken that problem and automated it, it's no longer your problem. And when you've got rid of your number one problem, guess what? Number two gets a promotion. Now, this is important. This is a process called emergence. It's what turns physics into chemistry, and what turns chemistry into biology, and what turns biology into sociology. And at each stage,